A computer system functions as an engine designed for a three-step cycle. It pulls raw data in, processes that data through a strict set of rules, and bursts back out with meaningful information. In computer science, we call this the input-process-output engine. To execute this continuous cycle, the engine relies on a clear division of labor between hardware and software. Hardware refers to the components you can touch. This is the physical machinery, like the silicon chips and circuits, required for computation. Software is intangible. It is the precise set of instructions that tells those physical parts exactly what to do. To understand how these two sides interact, we are going to build a mental model of a computer. We will start at the bare metal and stack the architecture layer by layer until we reach the interface you use every day. Circuitry remains a collection of static components until software provides the instructions necessary to activate the architecture. We begin at the execution core, the central processing unit. This central chip manages millions of operations a second, dividing that labor internally between two distinct processing nodes. The arithmetic logic unit handles the actual calculations. It is responsible for executing mathematical equations and logical comparisons. The control unit does not perform any math itself. Instead, it acts as a manager, orchestrating the flow of operations and routing instructions to the rest of the system. But for this core to process anything, data has to reach it first. This requires input devices, like a keyboard, which translate a human action into a data signal. Once processed, the results must exit the core to become meaningful to us. Output devices, like a monitor or printer, take that computed data and display it in a human-readable format. The CPU is efficient at calculation, but it cannot hold the data it needs to process all at once. Without a place to temporarily stage that data, the entire processor is bottlenecked. That staging ground is computer memory. This space is measured in units based on binary digits, zeros and ones, scaling from single bits and bytes all the way up to gigabytes and petabytes. The main workspace for the processor is primary memory, commonly known as RAM. This layer is directly accessible by the CPU, holding the active data for tasks currently running. Warning tone. But primary memory is volatile. It requires continuous electrical power to hold information. If the power drops, the data stored here is wiped clean. There is also a speed mismatch. The CPU calculates faster than RAM can deliver data. To bridge this gap, engineers placed a small, high-speed memory layer right inside the processor, cache memory. Cache acts as a high-speed buffer. By storing the most frequently used instructions right next to the processor, the CPU rarely has to wait on the RAM to fetch what it needs next. To solve the volatility problem, we rely on the final tier, secondary memory. This is non-volatile storage designed for long-term data retention. If a school needs to securely retain the academic records of 5,000 students, they cannot keep it in RAM. They must write it to this secondary storage layer, so the records remain intact even when the power is off. This long-term storage is often managed by hard disk drives, which use stacked magnetic platters to physically encode the data. Secondary storage also includes portable optical media, storing data via tiny physical grooves etched into the surface of compact disks. Together, the processor and memory array form a capable physical engine. But because the hardware communicates through binary voltages, it cannot directly interpret human language. To make the machine usable, we bridge that gap by laying a software stack over the hardware. Humans write instructions in programming languages that use recognizable words, but the hardware only executes machine code. Developers bridge this barrier using a software category known as language translators. Different languages require different translators. An assembler converts low-level assembly language into executable machine code. A compiler takes a broader approach. It translates a high-level program into machine code in one single batch before execution. By contrast, an interpreter translates code line by line while the program is actively running. Once the code can be successfully translated, developers can build application software, programs designed to perform specialized tasks for the user, like a web browser or a video game. But with multiple complex applications running at the same time, the system requires a central governor to manage memory and processor access so the programs do not conflict. That central governor is the operating system. It is the foundational system software, acting as the intermediary between the hardware underneath and the user applications up top. The OS operates as a resource manager, dividing its control across 5 distinct operational duties. Internally, process management allocates CPU time to different programs, while memory management continuously tracks and distributes RAM to active tasks. For data organization, file management structures the directories on storage drives, while security protocols protect that data via passwords and access controls. Finally, through device management, the OS uses specialized microprograms called device drivers. These allow the system to communicate with external hardware, like a printer. But the operating system also needs a way to accept instructions from the human operator. It does this through the user interface. Early systems relied on the command line interface. This lightweight, text-based format requires the user to use precise syntax to navigate files. In a CLI environment, executing even a simple file operation demands precise typed commands. To make systems broadly accessible, developers built the graphical user interface. Instead of typing commands, users navigate visually using windows, icons, and menus. By clicking a mouse to open a folder, the user performs the same directory operations as the command line, mediated through a visual abstraction layer. The operating system acts as the final interface, managing the complexity of drivers and memory while presenting a simple, clickable environment. To see exactly how this hierarchy functions, we can trace a single action down through the entire stack. Consider opening a program to type a letter for a business. The moment you click the icon, you interact with the application software layer. As you begin typing, the operating system allocates space in RAM to hold your active document data. Simultaneously, the central processor handles your keystrokes, pulling operational data through the high-speed cache memory to ensure your text appears on screen without delay. Underneath the interface, translators convert the word processor's commands into machine code so the arithmetic logic unit can calculate them. When you finish your letter and hit save, the operating system moves your data out of the volatile RAM and writes it to the secondary memory block. Once written to the storage drive, your document is physically preserved. Even if the computer loses power, your data remains secure. This engineered hierarchy manages the transition from human intent to machine execution. By tracing data as it cascades through these layers, we can see the exact mechanics that allow a modern computer system to function.